This is part B of concept video of section 11.3, integral test. So earlier we saw the requirement of an integral test. The function is continuous, positive, and decreasing on the interval 1 through infinity. Then the behavior of the series would be similar to the behavior of the improper integral. If the improper integral is convergent, then the series would converge. If the improper integral is divergent, the series would diverge. This improper integral only tells us that the series is convergent or divergent. It doesn't say where it converges to. Then we saw an example. The next type of series is the P series. So earlier in one of the sections, you saw geometric series. Next type that you're seeing is the P series. The P series, sigma, n varying from 1 through infinity, 1 over n to the power p, is convergent if p is more than 1 and divergent when p is less than or equal to 1. Comparing to the P series, we can say sigma 1 over n cube is convergent why the exponent is 3 and that 3 is more than 1. Therefore, it is convergent. Then sigma 1 over n to the power 1/3. Here the p value is equal to 1/3, which is smaller than 1. Therefore, the series is divergent. So after telescoping series, geometric series, we are seeing P series. This will be extremely helpful later on. And we also saw harmonic series. If you notice, harmonic series is sigma 1 to the power n, which is harmonic. But it can also be considered as a P series with p equal to 1. When it is P series with p equal to 1, we know that it is divergent because it's whenever p is less than or equal to 1, the series is divergent. We should not infer from the integral test that the sum of the series is equal to the value of the integral. In fact, sigma 1 over n square would be equal to pi square over 6, whereas the integral of sigma 1 over x square dx would be equal to 1. This can be done by improper integral technique. Therefore, sum of the series sigma an, n varying from 1 through infinity, is not equal to the value of the improper integral. Next example. Determine whether the series sigma ln n over n converges or diverges. We are checking whether the series ln n over n converges or diverges. Anytime you have ln n or e to the n or exponential, its integral test is a way to start. So we will apply integral test here. Apply integral test. Consider the relating function. F of x equal to ln x over x. The relating function should have x in it and not n. It's not, the domain cannot only be integers, it should include all values. So f of x equal to ln x over x. And then the requirement must be met. Requirement of integral test. F of x is positive, continuous, and also it should be decreasing. But first, definitely, we notice that f of x is positive and continuous. Is it decreasing? On 1 through infinity? In order to do that, we will compute the derivative. Or we are applying increasing, decreasing test by checking the derivative. So f prime max is denominator times derivative of numerator minus numerator times derivative of denominator divided by denominator square. So I'm looking at the function f of x equal to ln x over x and applying the quotient rule to find out the derivative. So it is ln x times 1 over x minus ln x divided by x squared. So it will be 1 minus ln x over x squared. This is f prime x. So denominator is always positive. So the numerator will be less than 0 whenever ln of x exceeds 1. So f prime x is less than 0 when ln of x is more than 1 or when x is more than e. So it follows that we only have to prove that f is decreasing eventually or ultimately. It's for every x more than e, then the function is decreasing because the derivative is less than 0. So we can say it is eventually decreasing. It follows that f of x is decreasing ultimately. When x is more than e. We proved that far. So now we are allowed to apply the integral test. So far, we have only proved the requirement of the test. So now we are going to apply the integrals test. We are going to evaluate the improper integral 1 through infinity fx dx. This integral 1 through infinity ln of x over x dx. So if you're right in terms of improper integral method, limit as t approaching infinity, integral 1 to t, ln of x over x dx. It will be limit as t approaching infinity. For this ln of x over x, we can apply the substitution method. So du equal to 1 over x dx. So we can write this as 1 to, we can substitute that later on because it's now converted to u. So it is u times 1 over x dx, that will be equal to du. So ln of x over x can be written as ln x times 1 over x. So that's exactly what we have done here. So this part du over x, dx over x becomes du. Now, if you integrate this, it is u square over 2. The limit is t approaching infinity. U square over 2. But what is u? ln x. ln of x the whole square over 2. Between the limits 1 and t approaching infinity. So it implies ln of t the whole square over 2 with the t approaching infinity minus ln of 1 and square, so it will be 0. So this part becomes infinity. Ln of t over 2 and t approaches infinity. This would be an infinity, which means that the integral, improper integral, diverges, and therefore the given series would also diverge. Thus, by integral test, the given series sigma ln n over n n varying from 1 through infinity diverges. Then from the exercise, for the suggested problems, I have done some in the videos for this section. So I have done problem number 8, problem number 21, and 25. So please refer to the videos for this section. Hope these videos help.